Hello, hi all. Welcome. My name is Kristoffer. I'm a software developer with Gradient Software, and I've been working on Gadgetron for a couple of years now. I'm here today to give you a very practical introduction to Gadgetron. I'll have a few slides concerning some of the types we'll meet along the way, but most of this talk is going to be a live demo. We're gonna run Gadgetron. We're gonna run the client. We're gonna talk about what's going on along the way. We're just gonna get entirely practical about how you run Gadgetron and how you do things. If you're already very experienced using Gadgetron, I doubt I can communicate anything really new to you in this talk. But feel free to stick around for the entertainment. If you want to, you can follow along at home with all the demo stuff. The resources I'm using are available on the site page. There's a link here in the slides. You should have access to the GitHub page. It should be easy to find. There's the dataset I'll be running and the visualizer script, and I think the config files are there as well. So if you want to follow along, feel free to do so. The materials are on the course site. The goal of the demo will be to run like a really simple example reconstruction where we take a very simple data set and produce some very simple images. The focus will be on how we interact with Gadgetron, how we make it do work for us. It's basically going to be a driver set 101. So I think Pierre is managing the questions. I might stop along the way and ask for like time-critical, pertinent questions. If I say anything stupid or there are like excellent questions that I need to address immediately, just break in. Otherwise, we might be able to handle a couple at the end. Before I get going, I would like to introduce the layout of the talk, sort of the windows we will be visiting. So if I start down here, the widescreen, to the left is my editor. In this editor, I'm gonna update the config file. We're gonna talk about what we're doing. We're gonna edit the config file. The config file lives here on the left. On the right here, I have an MRD viewer that allows me to examine MRD data sets. So we can have a look at the data set, we can have a look at the acquisitions, and hopefully, if the demo goes well, we can have a look at the images as well. So on this screen, there's going to be the config file and the viewer. Down here in the dark basement, I have two terminals open. Here on the left is where we're going to run the client. And here on the right, we're going to run Gadgetron. We're going to have a look at some of the log output as we progress through the demo. So left here is the client, and right is going to be Gadgetron. There's a fifth actor that's going to pop up when I run a chain. So I have written a sort of a fairly basic, silly little Python script to help me visualize what is in the Gadgetron pipeline at a certain point. So when I run a chain, it's going to pop up. It's going to have a window with a very basic pie plot. And hopefully it'll help me like visualize what's going on in Gadgetron. I will introduce that when we actually run the chain. You'll get to see it. So yeah, let's start with Gadgetron. So we are gonna go here to the right terminal, and we're gonna start Gadgetron. To run Gadgetron, you shout its one true name into the dark void, Gadgetron, and Gadgetron will show up and greet you. So we can see let me get you guys out of the way. So you can see it tells us a bunch of debugging information. So it tells us what port it is running on, and there's some like help for me when I need to help you. It tells me where it thinks all the things are, like debugging help. Gadgetron is a server. So this process is, so it's started, but it is just ready and waiting. There's no work for it to do. It's just sitting idle, sort of like an HTTP server. It's waiting for a client to connect and do some work. To get Gadgetron to like do work for you, the client needs to tell it two things. So the client needs to send a config file, sort of a program, a wish list. It's a specification of the chain that is to run. So the config file describes which gadgets in which order are to be assembled in a chain. Following the config file, the client sends an MRD dataset. And Gadgetron will then work its magic. When Gadgetron receives a connection, it reads the config file and it runs off to prepare the specified chain. So it rushes out on the disk. It finds the DLLs, the shared object files in which your gadgets are saved, and it loads the gadgets with the names you provide. It strings everything together in a chain, and it readies this chain for when the data arrives. And when data arrives, Gadgetron dutifully pushes the data through the chain as fast as it can. And any data, any items that leaves the bottom of the chain is then sent back to the client. When there's no more data, when there's no more work to be done, Gadgetron will then like clear everything up, pull everything apart, and go back to waiting. So it turns to this waiting state where it's ready to serve the next request. So we will just leave Gadgetron running here, and it'll take connections during the talk, and we will look at the logging output. Yeah, so this is a Gadgetron running. Let's go over here to the left, and let me introduce the client. I say the client. There's a lot of different clients. So Gadgetron just speaks like a standardized protocol, the MRD protocol. And any client that speaks that protocol can interface with Gadgetron. So Gadgetron ships with a command line client that we'll use. But like some scanners have their own client. I think there exists there's a Python client in existence as well. So this is by no means the only client. But we will use the one that ships with Gadgetron. Again, we just shouted into the darkness here. So this is the Gadgetron client. It selects the right port by default, and it calls your local host the local Gadgetron by default. So all we actually have to tell the client is which dataset to send and which config file to send. So I'll select the data type here, dataset here with the F flag, and I'm going to run this simple gray dataset. And then I would like to send this config file. So this command is a client command. It runs my simple dataset, and the config file we will be updating. It sends it all to Gadgetron. Gadgetron does things, and data might be returned to the client. Let's have a look. Let's try to run this. So a lot of things going on here. These windows, they are the visualizer. They'll pop up whenever I run the client. Right now, they're not very interesting, so I'll just close them. We'll talk about them when there's actually things going on. You see, Gadgetron actually gives an error here. We see Gadgetron, so it accepts a connection from localhost. That's the connection from the client. We see it like entering different states as it receives first the config file, then the data. And we see it connecting to the visualizer script. And then we see it produce an error. Not to worry about that. That's because the config file we're sending is pretty poor. And then we see it closing the connection again. So right now, our config file is pretty bad. We will fix that in a moment. But I'll introduce the data set first. So this command we're running, we'll reuse this command. We don't need to update the command. So we will update the config file throughout the demo, but the client command will stay the same. So we have two terminals in play here. Gadgetron is just going to keep running, and for the client, we're just going to run the same command over and over. So you don't need to be overly concerned with like updating the commands. That's already done. But let me introduce the dataset. For the dataset, we're going to go to the viewer. The dataset I've chosen is not terribly interesting. It's a fully sampled Cartesian dataset. There's 10 repetitions. Some like excellent soul in the NIH put a phantom in a scanner once. He made this really like excellent example dataset, and we're going to use that. It's fully sampled. There's no acceleration. It's Cartesian. We're going to be able to reconstruct it just using a simple FFT. An MRD dataset consists of two sort of main parts. There's a header, an XML header, containing a lot of information about the experiment. A lot of metadata, a lot of it tells you a lot about the scanner and what went on when the scan was made. So we can see it's a 1.5 Tesla Siemens machine. The dataset was produced in Bethesda, and there's a lot of interesting information here. So it has some Siemens artifacts as well. So it's oversampled in the readout direction, for instance. But yeah, so the dataset contains like the two major parts. The XML header is the first part, contains a lot of meta information about the experiment. And the second part is a bunch of data. The data consists of a sequence of acquisitions. Each acquisition essentially being a readout from the scanner. So each acquisition is a readout line. The viewer here, it's a bit messy, but like down the y-axis here is the scan counters. So every line here is an acquisition. I can select an acquisition and I get a plot of the data. And in the table up here is the header information. So an acquisition consists of the actual data. There's data per channel, and then a header that has a lot of stuff in it. I have a slide about the acquisition data type. So when you encounter acquisitions, the concept I would like you to think about, the concept I would like you to have in your head, is just that acquisitions model a single line of readout. As with all things, the reality is a bit more like detailed, complicated. But like the abstract concept at work here is just a single line of readout. It's an MRD data type, so it's supported by all the different clients, Gadgetron, like everywhere. That in turn means it's also easily stored. It's used extensively in Gadgetron, so it's very popular as input to the reconstructions. The config files available in Gadgetron, both because it's easily stored, and also because scanners tend to produce them from their clients. So it's used a lot. Like inside an acquisition is a header. The header is full of a lot of stuff. I could go into a lot of detail about what is in the header. So there's stuff that lets you, but essentially the header is there to let you know where the data in the acquisition belongs in your scan. The header of an individual acquisition contains enough information for you to place the acquisition line in your experiment. Like, you learn the details of the acquisition type by essentially working with it. There's also some data in an acquisition. There's a line of readout for every coil on your scanner. And then optionally, if you're doing non-Cartesian work, there might be a trajectory. But that's our data set. It's a simple, fully sampled Cartesian data set. All right, let's go to the config file. Let's see if we can't fix it, at least, so we don't provoke an error from Gadgetron. Let's start with the error. The error is that Gadgetron is not currently set up. The config file hasn't specified that the data set is going to come in the form of acquisitions. In fact, the config file doesn't specify anything. So Gadgetron, after receiving this config file, is not prepared for any input at all. To rectify this, we will add a reader to the config file so Gadgetron knows how to receive acquisitions. To add a reader, we'll start with the readers block. So a reader lives in readers. To add anything to a Gadgetron config file, you have to tell Gadgetron what class you're interested in and where Gadgetron can find it. So we have to specify a class name, and we have to specify a shared object file, a DLL, where Gadgetron can find this. We have to come up with a class that knows how to read acquisitions. And I'm going to go out on a limb here and use an acquisition reader. It seems like a good choice. The acquisition reader class is found in Gadgetron core readers. Finding documentations about where the gadgets live, what they do, there's some excellent resources, but it's going to be a bit nebulous for now. I'm just going to pull these basically out of my brain. But we've added an acquisition reader now, so Gadgetron should be able to receive acquisitions now. So basically, the client connection is going to come in. The reader is going to read the binary data from the connection. It's going to turn the acquisition data into individual acquisitions in C++ space. And these acquisitions are going to flow into the stream. So this stream is like the sequence of gadgets. You'll see I've already placed this external node here that connects up to the visualizer script and just sends all the data out there. So if we run this config file, we expect the connection to come in. We expect the connection to come in. We can expect the acquisitions to show up. The reader will read them, stuff them into the stream. Nothing in particular is going to happen to them. They're just going to get forwarded to the visualizer where we can have a look. So I'm going to go down to the left here, and I'm going to rerun the client. We see over here in the Gadgetron log, we see it accepts a connection, and we see it connecting to the visualizer, and we see Gadgetron pausing. It's waiting for the visualizer, it's waiting for the streams to close now. We have fixed the error, it appears, and that is really very excellent news. When I push, so the visualizer has one button, it's this next button. And when I push the next button, the visualizer is going to consume an item from its input queue, and it's going to make a very basic plot here in the plotting window. So if I click next, the first acquisition is consumed, and it is plotted here. Well, I plot the first channel, and I plot magnitude. Second acquisition, the third acquisition. We can bring this up to the visualizer and have a look. So this is actually We can verify that we're just in Gadgetron here. We're just seeing the acquisition data in the stream now. If I pick the next acquisition, I see the next acquisition. If I pick the next acquisition, I see the next acquisition. Oh, sorry, next acquisition. So at the moment, we receive acquisition input, and the visualizer lets us step through it and have a look. All right. To construct an image, we have to do a number of steps. We have to essentially bundle up our acquisitions. We have to find the acquisitions that go into a single repetition. We have to bundle those up. We have to assemble them into a k-space buffer, and then we're going to do an FFT on that buffer to get an image. The first step of that plan is to simply bundle up acquisitions. To bundle up acquisitions, we're going to use a gadget that bundles up acquisitions. To add a gadget, I'm going to put a gadget in my stream. For Gadgetron to do anything useful, we have to tell it which class we're interested in. To bundle up acquisitions, we're going to use a gadget called acquisition accumulate trigger gadget. Let me close this. Acquisition accumulate trigger gadget. And we have to tell Gadgetron where it lives, of course. This one lives in Gadgetron MRI call. Gadgets. Spelling is hard. So at this point in the stream, start of the stream, the reader is producing acquisitions. So we have acquisitions here. Acquisition accumulate trigger gadget is gonna consume acquisitions. It works by examining the headers, and whenever some trigger condition occurs, that's the trigger in the name, trigger. Whenever some condition occurs, it's gonna take the bundle of acquisitions that is already accumulated, like set aside, and it's gonna emit that on the far side. So after acquisition accumulate trigger bucket, we no longer have acquisitions. We have the type it emits. It's called acquisition buckets. So the type is called acquisition bucket. We have acquisition buckets. Acquisition accumulate trigger gadget is a highly configurable gadget. So you can basically set it up to look at any of the stuff you find in acquisition headers. So it's very configurable. You can get it to like bundle and slice your data any way you like. We would like it to look at this field, the repetition field. And whenever that changes, like whenever we switch to a new acquisition, whenever the acquisitions are part of a new repetition, we would like it to emit the bucket it was constructing and start a new bucket. So we get the repetitions nicely separated into buckets. To specify this behavior, we set a property on the gadget. So properties in general, they're a way that you can modify gadget behavior. We're going to just use this one because we are pretty happy with the default behavior. But most gadgets are configurable in at least some way. The property we're going to set on acquisition accumulate trigger gadget, it's not, yeah, name. So the property we're going to set is what is trigger dimension. Trigger dimension. And the value is going to be repetition. So this tells acquisition accumulate trigger gadget to watch the repetition part of its incoming acquisitions, and whenever it changes, it needs to release the acquisitions it had accumulated so far. So that should give us some nice buckets here out on the outside. This gadget, acquisition accumulate trigger gadget, is like it's very, very common in Gadgetron. It's part of the default way to go from acquisitions to case-based buffers, and so it's found in a lot of reconstructions. I tallied the config files that ship with Gadgetron, and it's used in 44 out of 64 of those. So it's very common. But I mean, let's run this. Let's see what we get. So same command here. Just gonna rerun it. We see out here. We see changes in the Gadgetron output. So we see logging output from acquisition accumulate trigger gadget. We see the usual connection established, the visualizer connection. And then we see acquisition accumulate trigger gadget sending out a bucket. So it sends out a bucket every time it has received a repetition. If we click next in the visualizer, we should get a nice plot of a bucket. I wasn't entirely sure how to visualize a bucket. So I just plotted all the acquisitions in a bucket. So this is sort of an edge-on view of a case-base, if you like, or you could think of it as just a lot of acquisitions plotted on top of each other. Let's go into some detail of the bucket data type. I have a slide. So the acquisition bucket type, what I'd like you to think about when you hear acquisition bucket is a collection of acquisitions. It's a nice loose bundle. They're not ordered, they're barely sorted. They're just sort of picked up as they come to acquisition accumulate trigger gadget, and they're just set aside and released in a nice, bundle is the best way I can describe it. A nice, loose, flowery bouquet. In contrast to acquisition itself, the acquisition bucket data type is not an MRD data type. That means you can't, by default, send it to MRD clients, so your scanner won't understand it. It's also not easy to save in H5 files. It's a type that is used like internally in Gadgetron. So it's a type that will exist in the gadget chain between gadgets, but they'll never be saved anywhere. It's an intermediate type. Very, very frequently, this type is immediately converted into recon data. That is the next step of our reconstruction as well. So we will get there in a second. So an acquisition bucket, like in detail, it contains a collection of acquisitions and a collection of reference data. So acquisition accumulate trigger gadget looks at your acquisitions, and if it determines that they are in fact reference data and not data acquisitions, it'll set them aside, keep them in a different collection. And it may contain some waveforms that were received by acquisition accumulate trigger gadgets while the bucket was being accumulated. So this could be ECG data or whatever waveforms you're sending. But buckets, conceptually, they're just a very simple collection of acquisitions. So our chain now, it receives a connection. The reader lets us read the data, the acquisitions of the connection. The acquisitions enter the stream. They're consumed by acquisition accumulate trigger gadget. And acquisition accumulate trigger gadget outputs a bucket every time it has received a full slice. And these buckets, as the config is right now, then enter the visualizer and we can have a look. If we click next, we can see the next bucket. I don't know if you can see the changes. I'm not sure how much you can see through Zoom. But I see the bucket plots changing slightly. We have 10 buckets because we have 10 repetitions. As I consumed the final bucket, Gadgetron realized it was finished. There were no more data to process, and it closed down the stream, and the client returned. So that's the status as it is. Let's take these buckets and let's assemble some k-space buffers. Yeah, let's do that. So to take a bucket of acquisitions and turn it into like an assembled k-space buffer, like a single array with all the data ready for work, say an inverse FFT, we're going to add a gadget to do this. We're gonna add a gadget that's called bucket to buffer gadget. This gadget is also fairly configurable. We'll return to that. And bucket to buffer and acquisition accumulate trigger gadgets, both gadgets are very, very often used together. So in like very often, acquisition accumulate trigger gadget is followed directly by bucket to buffer. Buckets are rarely used alone. I mean, the only use case that I see at least reasonably frequently is for high performance MATLAB interfacing. Apart from that, buckets are almost always converted straight into k-space buffers. Bucket to buffer gadget, it lives in Gadgetron MRI core. Like if you have to make a guess, Gadgetron MRI core is not a bad guess. So bucket to buffer is going to consume a bucket of acquisitions, and it is gonna take the individual readout lines from the acquisitions. It's going to look at the headers. It's going to figure out where the readout in the acquisition, where it goes in k-space, and it's going to assemble the k-space buffer. Yeah, so let's make a note here. Bucket to buffer will output recon data. That's the name of the type. We'll have a look at that in a moment. Let's run this first. Let's see if we don't get some nice k-space output here. So we see the client run, and we see Gadgetron take a connection. We see the same output from acquisition accumulate trigger gadget every time it outputs a bucket, and we see some output from bucket to buffer. So this is bucket to buffer, like taking a bucket and sending out a recon data buffer. If you look at the log, you see acquisition accumulate trigger gadget sending out a bucket to buffer immediately picking it up and outputting recon data before acquisition accumulate trigger gadget has sent out the next bucket. So this is the two gadgets. This is acquisition accumulate trigger gadget and bucket to buffer working concurrently. So bucket to buffer is building k-space buffers while acquisition accumulate trigger gadget is like bundling up acquisitions. This all happens concurrently, and it is delicious, to be honest. If we click next in the visualizer, we can consume the first recon data item here that's currently waiting in the input queue to the visualizer. So I can click next, and we get a delicious naive plot of k-space here. I don't know how much you can see through Zoom, but if I click next here, I get the next k-space buffer, and I can see changes, but they might be filtered out for you guys by Zoom. So yeah, at this point, we have client connection. A reader produces acquisitions. The acquisitions enter the chain. Acquisition accumulate trigger gadget assembles some buckets. The buckets are turned to k-space buffers, and we are visualizing the buffers. Yeah. Did I forget anything? I did not. So let's have a look at the recon data. The recon data type is by far the most conflict data type that we will touch today. I want you to think of it as just an assembled k-space buffer. It's not an MRD type. So like bucket, it's an intermediary type. But unlike bucket, it's a very popular type in Gadgetron. So there's a lot of gadgets that either consume it as input or produce it as output. Basically, every gadget operating in K-space probably touches recon data in some way. It has, like, it's been in Gadgetron for a long time, and it has a lot of stakeholders. It's used in a very many contexts, and as a result, it has picked up like a lot of eccentricities. So if you were to take a look at what is actually in the recon data type, you'd see. So I have some dots here because I can't put the entire tree here. There's a lot of stuff in there. What is important is that for every encoding space, there is a data buffer, and this is like a 7D general purpose K-space buffer. So encoding spaces, you're usually going to see one. There's some applications that have more than one encoding space, but one is by far the most common occurrence. So recon data sort of, I want you to think of it as a K-space buffer. I want you to think of it as basically just this 7-dimensional K-space buffer with some headers attached and some like additional information. The 7 dimensions in this data. So there's a readout dimension, and then there's 2 encoding dimensions, and then there's channels, and then there's 3 general purpose dimensions here: NS and lock. If I were to go to bucket to buffer gadget here, I could add some properties. I could configure it, for instance, to put repetitions along the n dimensions. So if I sabotaged acquisition accumulate trigger gadgets to like accumulate all the acquisitions in a single bucket, it's easy, I just remove this property. I could configure bucket to buffer to fill up the recon data buffer with repetitions in either n or s, for instance. So bucket to buffer gadget is configurable. It lets you sort of control what goes into these general purpose dimensions. For us here in this example, we have 1 repetition per bucket. So we use the readout. This is 256 due to the oversampling, and then we use the phase encoding dimension here. So that's 128. And I think we have 32 channels. Like every other dimension is a singleton. It's just one. Yeah, but so it's a complicated type. You learn the details by working with it. Once you master it, you can talk with every Gadgetron, it feels like. But when you encounter it, just think of it as an assembled K-space buffer. That's my best advice. So at this point in our reconstruction, we have actual K-space buffers. Yeah. Let's take these K-space buffers. Let's do some FFT. Let's see if we can't make an image. To make an image, we're going to add a gadget that makes images. There we are. We're going to do a very simple reconstruction. So we're going to use a gadget called simple recon gadget, I think. This gadget is used like very little in real life. It doesn't do a lot. So it just does an inverse FFT, and then it combines the channels through a simple like sum of squares. So it's not very exciting. It doesn't do a terrible, like it doesn't do a lot of work. but it's used a lot in examples, and that's why I'm using it today. It's a very simple gadget. It lives, perhaps unsurprisingly, in Gadgetron MRI core. It takes a recon data buffer and does the Fourier transform along the first 3 dimensions, and it outputs something called an image array. We'll have a look at those in a second, but let's run this, see if my typing is up to scratch here. So Gadgetron is ready. We'll run the client. And so when we examine the output of Gadgetron, we see no additional logging output. That's because simple recon is actually fairly client. It doesn't produce any output. But I am fairly confident it ran. So we should get images. Hallelujah! Demo makes images. So this is an image of the phantom. This is our, along the y-axis is the readout direction, and the phase encoding is on the x-axis here in this plot. If I click next, we get the next repetition. Next gives us the next repetition. Let's go into some details about the image array type, I guess. Image array is not images. I would like you to think of it more as an image buffer. So it has the same 7-dimensional layout, only conceptually it's in image space. So it's not an image in the same way that K-space is not an acquisition. Think of it more as an image buffer. It's not an MRD data type. You can't store it. You can't actually send it to the client. So even though it's a data type that contains images, it has all the data you need to like display and work with images. It's not a standard type, so you cannot send it to clients. It exists only in Gadgetron. It is used widely in Gadgetron. It's sort of it serves as a recon data type only in image space. It's sort of a parallel type. It's a reflection. So it shares like this 7D data array, but the dimensions now in image space. So there's an X, Y, Z direction in the image. So you can have 3-dimensional images, and the image can have a number of channels. And these NS-log dimensions, the general purpose direction dimensions, are the same as for recon data. They're generally preserved. In an image array, there's also an array of image headers. There's basically, so an image is like the first 4 dimensions. So there's an image header for each image, basically. There might also be some metadata strings and some waveforms, like a lot of stuff. So it will contain maybe acquisition headers, so you know which acquisitions went into producing your image data. There could be some waveforms. It could be a lot of things in the image array type. Conceptually, it's just a buffer of image data. At this point, we receive acquisitions. We accumulate them into nice flowery bouquets. We turn the bouquets into delicious K-space buffers. We do some simple processing of these to produce some image data, and then we visualize the image data. As image arrays are not standard MRD types, we can't send them back to the client. If we could, we would essentially be done. Now we just have to sort of make them flow back to the client. But as they're not standard, we can't actually do that. So we have to turn our image arrays into actual images. To do that, we're gonna enlist the help of a gadget. This gadget, it has a name, I'm pretty sure. Image array split gadget. There's sort of a naming, I won't say it as a naming convention, but it's pretty often it's a noun verb gadget is a good guess. we're going to call for image array split gadget, and we're going to say it lives in MRI core. Gadgetron MRI core. So image arrays can contain multiple images. So there's an image header and a lot of image data, up to 4-dimensional, but there could be a lot of images in an image array. If I were to, going back to the example, if I were to have all the acquisitions in a single bucket and have a case-based buffer that contained repetition along the N or S axis, I could still just pass it to simple recon gadget and it would produce images. It would consume this easily. But I would have a buffer here with 10 images in it. Image array split gadget, it takes such a buffer containing multiple images and it explodes it into individual images. As of right now, we just have a single image in our image arrays. That's what makes them like easy to plot. So it's just, it's basically, it's going to transform a single image in an image buffer to just a single image. So it's basically just going to do type conversion for us. But if we had a lot of images in the image array, it would explode them. On the other side of image array split gadget, we're going to have just images. I'm going to add complex here because the image data in the image arrays is complex data. The image data in the images are going to be complex data. But this image array split gadget is going to take an image array. It's going to split the single image into a single image, and the single image is going to flow into the visualizer where we can have a look. Let's see if I managed to spell everything correctly. This is not a great increase in logging output. So this is pretty much the same. We're using some very quiet gadgets here late in the chain. If I click next, I consume like the first image available to the visualizer script. So we're no longer seeing image arrays, we're seeing images. I've transposed the image, so the readout direction is along the x-axis. If I click next, we see progressively we see the images, and there's 10 of them. That's always good. Yeah. So far, so good. The image type conceptually is a single image. It is an MRD data type. It's supported by the client. We can send it to all the clients. We can store it, and it's used quite a lot in Gadgetron. It's like typical output. So there's a lot of reconstructions. They take acquisitions and they produce images. So the image data type, it's an MRD data type, and it looks a lot like acquisitions. So there's some data. Images are 4-dimensional, so there's an X, Y, and Z direction. There's some channels, and then there's a header, same as for an acquisition. The header fields are different. So an image will like specify image type and timestamps and field of view and like a bunch of other stuff. And then there's an optional meta string. So it's like the model concept is like a single image, kind of like acquisition is a single acquisition. And the two types there, they share a lot of things. It's no longer an intermediate type. You can send these to the client just fine. So our next task is actually to make sure these images, so right now, Gadgetron just receives all the data, does a lot of processing, it creates the images, and it sends the images to the visualization script. And the visualization script, it takes the images, it says, oh, nice images, let me plot those. And then it gobbles them up, it puts them into the plot, and then the data just sort of disappears. So to send them back to the client, we need the images to like exit the bottom of the stream here, and we need to have a writer that can write them to the client. So we have some tasks ahead of us here. There is the added complexity that the viewer here, it doesn't display complex images very well. So I'm gonna add a gadget real quick that takes complex images and creates magnitude images. So class name, sorry, typing class name. This gadget, I'm gonna use complex to float gadget. There's a number of gadgets to do this in different ways, and you can convert to different types. We're gonna use this one. And surprisingly, this gadget lives in MRI core. So that takes an image and turns it into a magnitude image, a real image. Let's run this. Let's see if the images are still images, I guess. That is so lucky. All right, we have images. Cool. Let's see if we can't send these back to the client. So the first thing we do is we have to sort of sabotage the visualizer, because the visualizer is not playing nice. It's just consuming everything we send to it, and it goes missing in the void of dev null. So now without the visualizer, the images, they hit the bottom of the stream. When an item, basically anything, like every type, any item. Sorry.
Maybe Kristoffer, one thing is a lot of people are asking questions about the how to rerun the demo. And can you show the third terminal that runs the Python gadgets? Just to be clear that everyone that you need to read.
Yeah, sure. So down here I have this is the skunk works. I have a terminal running Emacs and I have running the viewer. And over here is the visualization script.
Thank you.
So in this folder, there's the visualization script and the Gadgetron logo. So to run it, I just run it. So it's a Python script. I just run it in Python, and the visualizer starts. It doesn't output anything. It's just sitting there waiting for Gadgetron to connect to it. Once Gadgetron connects, it will spawn a few windows and do like visualizer things. So to run the visualizer, just run the visualizer, I guess. I mean, we could do more questions, I guess. Or I can continue. So status in this config file, we receive acquisitions. Acquisitions are accumulated into nice bouquets. Bouquets are turned into, sorry, I'm scrolling around wildly here. Bouquets are turned into nice k-space buffers. The k-space buffers are reconstructed, simple inverse FFT. And the output buffers are exploded into individual images. We convert the images to real magnitude images so we can see them in the viewer, and the images hit the end of the stream. When an item hits the end of the stream, Gadgetron picks it up, it looks at it, and it asks the readers, the writers available to it, it asks its writers if any of them knows how to write this data type back to the client. And currently, our writer set is completely empty, so Gadgetron will get no answer. And when it can find no writer to write an item to the client, it'll just sort of shrug and discard the item. So to have the images written back to the client, we'll have to add a writer. Writers live in writers. So let's see if we can add writer close. All right. So a good image writer could be image writer. And I think image writer lives in Gadgetron core writers. That seems reasonable. So now Gadgetron should be able to find a writer willing to write images back to the client. So acquisitions go in at the top, they're accumulated, they're turned to case-based buffers, they're reconstructed into images. The images are split into individual images. The images are processed into magnitude images. These images reach the end of the stream where Gadgetron selects a writer for them, and the writer writes them back to the client. If we look at the client output here, we see that if it receives any output from Gadgetron, it'll write it to out.h5. If I show you what's in the folder, we make sure that there is no output at the moment. But if we run the client, we expect to see some. Hey ho! Suddenly we have output. So I can run the viewer and I can have a look at what's in this output data set. You can see there's a data set. It's named after now, and it has some images in it. So these are the images, and there's 10 of them, and they're almost the same because that's the nature of this data set. But that is full circle on this reconstruction. We tell Gadgetron through the config file that we would like to receive acquisitions. The acquisitions sent by the client are read by the reader. They enter the top of the stream, where they are consumed by the first gadget, acquisition, accumulate, trigger gadget. Buckets, case-based data, turned into images, split, processed, sent back to the client. So this sort of structure in config files. So this particular config file is sort of an example. It's a bit like it's short and there's not a lot of gadgets, but the structure is very common. So you will very often see acquisition, accumulate, trigger, and bucket to buffer together. Before those, there's like space for gadgets that process acquisitions. So there's gadgets being noise adjusted. There's a gadget that removes the seam and oversampling that like makes the image really broad. You could have coil combine. It's like a number of gadgets that operate in acquisition space. So there's like room at the beginning of a chain for a lot of gadgets that process acquisitions. And then you hit like these two guys, and they sort of lift you into assembled case-based buffers. And there's a number of gadgets that operate on the case-based data. And then you hit some sort of image reconstruction data that takes you into image space, where you have a number of gadgets operating on the images before they're sent back to the client. So it's not always the case. You're not forced to do this, but it's a very common structure in the config files. You could, just as a like short example, you could have an image reader here, and you can do an image-to-image stream. It's just acquisitions to image with these guys. It's very, very common in Gadgetron. So that's it for the live demo. It's time for questions, if you have any. I'd like to add that so I know these gadgets exist, and I just sort of invent their names and add them to the config files. When you're starting out in Gadgetron, it's very hard to know which gadgets are available, what they do, how to configure them, and how to sort of get what you want out of Gadgetron. So I would like to recommend some resources to sort of get started. We have a wiki page on GitHub where you can find at least an introduction to some of the more common gadgets. You're also really very welcome to ask questions on our Google group. And on our Google group, and there's a weekly meetup. It's not every week, so we are interrupted by like bank holidays and stuff, but it's almost every week. And showing up to the weekly meetings to ask questions is like an excellent way to like get through some of your particular issues. The invitation for the weekly Gadgetron meetup is usually posted in the Google group. But if any of you have any questions, I guess we can handle those. I think I might have a few minutes.
One of the questions, Kristoffer, is where can you find the list of gadgets that are existing already?
So I would go to the wiki. That has a list of the most common gadgets. If that doesn't serve you, you might, like asking is a good way to go about it, or actually looking at the Gadgetron source code is another way. I'm not sure there is a complete list in existence. Yes.
There are questions also about what kind of readers and writers do we have?
So Gadgetron has a pretty full set of readers and writers. So we of course have readers and writers for all the official MRD types, but we also have readers and writers for pretty much all the types commonly used in Gadgetron. So you can, if Gadgetron is talking to Gadgetron, it can send recon data, it can send buckets. So all the types I've mentioned here, we have readers and writers for those. So Gadgetron itself in the C++ landscape, you can send pretty much any type you like. You don't need to do any work. But if you want to communicate a type with MATLAB, Python, or like your own client, you need a reader and writer. But Gadgetron ships with readers and writers for all the common types, at least all the types I've mentioned. All right.
Thanks, Kristoffer. Yeah, it was a difficult job to present all the concept and do it well. We're going to do a small break for 10 minutes, and then we come back for doing the tutorial and the practice in Python. So the Zoom is still working, so you can just wait or have a break.
Hi, Kristoffer. Nice talk.
Hi, thanks.
Can I read a question from, or perhaps Niels, if he's around, can just ask his question about splitting data?
Yes, sure. I was going to go through the Slack channel and answer all the questions. But, I guess read.
Is Niels there to ask it, or shall I ask it?
Ask it, Oliver.
I'll ask it. So it says, I have a question about k-space handling. If you have a time series of several repetitions and want to split it into separate time series, for example, every second repetition, would you do that in the acquisition accumulate gadget, or would you modify this gadget?
So acquisition accumulate trigger gadget is configurable, but not that configurable. So I think you need to do something custom to make that work. So yeah, you need to edit some code.
That's cool. Yeah. So that would be going into C++.
I mean, you can. Sorry, touching the microphone. So there is like an overhead for going to Python or MATLAB, but you can definitely do this in either. So if you're not comfortable doing your accumulation, if you're not happy with the functionality in accumulate trigger gadget, it's fairly easy to write a Python gadget that does exactly what you want, and there's not a huge performance overhead for having it in the chain. Like, I'd be wary if you're doing like real-time stuff, but otherwise you can go pretty far with just writing a thing in Python that does exactly what you want it to do.
And I think we're going to see something quite similar to that in the next talk as an example.
Yes, so I think Valerie has a lot of Python lined up for everyone.
That's great.